In this video, I'm going to go over nodal analysis and the steps for performing it, and then do an example. So nodal analysis is pretty much just a standardized circuit solving technique, and it just employs the use of Kirchhoff's laws and Ohm's law. And the nice thing about it being standardized is that you can perform the same steps to solve pretty much any circuit. So let's get started. Okay, so first, step one is to pick a reference node, which is the same thing as ground. So the reference node is just going to be where you're going to define the voltage to be zero. So normally you're going to be given this, and it's given by this ground symbol right here. It's like the three lines. So we're just going to say this is ground, so its nodal voltage there is zero. Now step two is to place a nodal voltage at every other node. So you're probably also going to be given these in all your problems. So you see in this example, it gives us a 1, a 2, and a 3. So literally all we're going to do is we're just going to define V1, V2, and V3 at those nodes. And normally they'll just give you V1, V2, V3. So you don't really have to do anything for this step most of the time. And nodal voltage just represents the voltage with respect to the reference node. Okay, so here V1 just represents the voltage with respect to this zero and just to the ground. Same thing for V2, V3, because you can't have voltage at a single point. That doesn't really make any sense. Voltage is always between 2 points, the potential difference between 2 points. So that's what these nodal voltages represent. Yes, they're at a point, but it represents the voltage with respect to the reference node. Now, step three is to label and assume a direction for all currents. So here you just look at the circuit, and like, for example, right here, that one's not labeled, so we're just going to call it I1. Why not? It doesn't matter. And the direction is completely arbitrary. It doesn't matter which direction you pick, so just choose whatever you want. And then we'll call this one I3. Now, obviously, there is some current flowing at each one of these. And if the direction you picked is wrong, then if you were to solve for this I1, I2, or I3, then it would just come out to be a negative number. But if you assumed it the correct direction, it'll be positive. So now step four is to perform KCL, which is Kirchhoff's current law, at each nodal voltage. And then step five is to define all of the currents in terms of voltages. And the way you're going to do this is using Ohm's law. So I'll do a quick example of what this means. So let's say you had some setup that looks like this. Let's say you had a node here, V1, and a node here, V2. This resistor has some resistance R, and let's say you chose a current going this direction. So now to define the current in terms of voltages, for this example, you would say I equals V2 minus V1 over R. So every time you have something like this, you're going to see where the current starts. It starts at V2, so V2 is going to be first, and then it ends at V1, so then minus V1, and then you just divide by the resistor value. Now, this formula comes from the fact that current always flows from a higher potential to a lower potential. So you can say I equals V high minus V low over R. And you might say, wait a minute, if we just chose a random current direction, how do we know that it'll all work out? Because we don't know which node has a higher voltage. And that's true, but again, it doesn't really matter. When you pick a direction for the current, and then you need to define that current in terms of voltages, just always do the one the current starts with minus the one it ends at divided by the resistance. As long as you're consistent in writing your currents in terms of start minus end over R, then everything will all work out in the end. So just stay consistent and always follow that convention. So now that we have all of these rules in place, let's continue this example. So we already decided that this is just V1, this is V2, this is V3, and then we chose the currents to be I1, I2, and I3. So we've already done steps 1 and 2. We've picked a reference node, they gave us the ground. We've placed the nodal voltages, and we've labeled and assumed a direction for all the currents. So that's all the first 3 steps. So now we're going to do step 4. We're going to perform KCL at each nodal voltage. So you can just say KCL and then start with V1. Now remember, KCL just means sum of the currents in equals sum of the currents going out. So if we look at V1, we have 4 going in equals an I1 going out plus an I2 going out. And then you do the same thing for V2. We've got I1 going in plus 4IX equals an IX going out. And you can just rewrite this real quick as I1 plus 3IX equals 0. So now for V3, we have an I2 going in equals I3 plus 4IX. Now that is all of the KCL. So now we're going to do step 5, which is Ohm's law. So remember, the point of this is to define all of the currents in terms of voltages. So let's just start with I1. And now if we use our rule, we start, the starting voltage is just V1. It ends at V2, and it goes across a 3 ohm. So we can say I1 is equal to V1 minus V2 over 3. And then we can do the exact same thing for I2. It starts at V1 minus, it ends at V3, divided by 2. I3 equals V3 minus 0. This I3 goes from V3 to ground and ground to 0. So V3 minus, it ends at 0, still divided by that 6 ohm resistor. Now the only current left is just this IX they gave us in the problem. And that one's going to be equal to V2 minus 0 over 4. So now with these equations, we have all the information we need to solve the problem. The last thing we're going to do is we're going to plug in all of these I values into all of the KCL equations. So for I1, every time we see an I1, we're going to plug in V1 minus V2 over 3. Same thing for I2 and I3. Okay, so I'm just going to clear up some space. So we'll just start with the first equation. 4 equals I1, which is just V1 minus V2 over 3, plus I2, which is just V1 minus V3 over 2. And then we just need to simplify it. So the fastest way to do that is to multiply by a number that'll cancel out all the fractions. So we can just multiply by 6, and then we'll get 6 divided by 3 is 2 times V1 minus V2, plus 6 divided by 2 is 3 times V1 minus V3. Then just simplify further. And then just combine your like terms. And that gives us our first equation. Now we have 3 nodal voltages, so we're going to need 3 equations to solve for 3 unknowns, which is perfect because now we're going to find the second equation. So we're going to plug into this V2 KCL. So I1 is V2 over 3 plus 3 times Ix, which is just V2 over 4, equals 0. So now we can multiply this entire equation by 12. 12 divided by 3 is 4 times V1 minus V2, plus 12 divided by 4 is 3, times 3 is 9 V2 equals 0. So then we just combine like terms. And we end up with 4V1 plus 5V2 equals 0. So that is our second equation. Now, the last one, I2 is just V1 minus V3 over 2, which is equal to I3, which is V3 over 6, plus 4 times Ix, which is V2 over 4. And we can multiply this entire equation by 12 again. And 12 divided by 2 is 6. V1 minus V3 equals 2V3 plus these 4's cancel. We're left with 12V2. Simplify further. 6V1 minus 6V3 equals 2V3 plus 12V2. And then you can combine like terms again. And you get this equation as the final one. So now the last step is just going to be solve equations 1 through 3. Now you can do this any way you want. Ideally, you'll use a matrix calculator or something so you don't have to just do all the algebra. I'm sure you already know how to do algebra. So if you just plug that in, you will end up with V1 equals 32 volts. V2 equals negative 25.6 volts. and V3 equals 62.4 volts. And that's an example of how you can use nodal analysis to find nodal voltages.